Swayam Prabha. Digital India. Educated India.
So, so what we want to prove now is what is called crossing. It's a theorem, but people call it crossing lemma. Okay. There are originally due to so I forgot. Lytton was the one who did it. Then let me check the reference whether I've written the reference. Yeah. So Lytton had a proof in 81. Then Aitai, Chattal, Newborn, Semered-D in 82. These all were involved proofs. Okay, the current proof is from proofs from the book. Do you know this book? It's a very popular book on mathematics. So, like classical results of classical, non-classical also, some of the results proved in a very nice way. Okay, and this result is from that book. Okay, so the proof is from that book. Okay, so where we basically show if the number of edges in the graph is greater than 4 times the number of vertices, okay, then the number of crossings in the graph G. So let me say the graph is vertex set and edge set is omega of cube of the number of edges by square of the number of vertices. See, if you use results from just that planarity result for graphs or Euler formula on the plane or stuff like that, you can never get a nonlinear bound like this. So think what is this saying? If the number, select the number of vertices in the graph be n, okay, and this is the number of edges is like n square, okay, dense graph. Average degree of the vertex is some omega n. Okay. Then what is this saying? The number of intersections will be, whatever drawing you do, the number of intersections will be n to the power 4, right? But or n to the power 4 or size of the number of vertices to the power 4. But so for the planar graph, the result that the bound that we get, that number of edges is less than equal to 3 times number of vertices minus 6, that follows from this result for planar graphs. Okay, there is a notion of faces and edges in planar graphs. So what you can show is number of vertices minus the number of edges plus number of faces is equal to 2. Okay, you use this result and another inequality which is like twice the, so number of this is greater than equal to 3 times the number of faces or something like this. You use these two to get that bound, okay, of number of edges being less than equal to 3 times the number of vertices minus 6. Okay, but this bound is very hard to get using these kind of linear relations which are linear in edges and vertices. Okay. So here the main new ingredient is probability. Okay. So again, let's go back to the original proof again, the previous proof. So how did we start? You are given a graph v comma e. You have drawn it on the plane in such a way that it has exactly CRG many crossings. So drawn with exactly CRG many crossings. So now what I do is the following. So let P be a number between 1 to 0. Okay. What I do is I will sample the vertices of the graph. So, what do I mean by that? And I will sample it independently, vertices of the graph. So, what do I mean? I will select a vertex with probability p. So, what is the probability of not selecting the vertex? 1 minus p. So, the vertex set I will denote by the selected vertex, I will denote by Vp. Vp is the set of vertices selected from V, where each vertex is picked with probability p. Okay. Is it a fixed set? Is Vp a fixed set? What is the probability that I did not select any vertex? For a particular vertex not selecting is 1 minus p. I am saying what is the probability that Vp is empty? Vp can be empty or Vp is a fixed set. It is a random experiment, right? It is not a fixed set. It is a distribution over subsets of vertices, right? The way we are doing it, it will give you a distribution over the subsets of vertices. So, what is the probability of not picking any vertex? Any vertex, none of them were picked. 0. 1 minus p to the power n, right? Here what are you using? Independence, right? Okay, good. So it's a random. So basically this is a random variable. Like size of Vp will be a random variable. Okay, it doesn't have a fixed size. It gives you a distribution. Okay. So what is the expected value? So I will denote it by this expected value. So what is the expected value of size of Vp? This is equal to, because each vertex is selected with probability p. Okay. Good. Now, so we will be building a graph GP with vertex set Vp and S set EP. Okay. So if let us say there was an edge between 1 and 2, vertex 1 and 2, and both 1 and 2 got picked, then the edge 1, 2 will be included in EP. Okay. Is EP a fixed set or not a fixed set? EP will be determined by Vp. Vp is not a fixed set. So EP cannot be a fixed set also. Okay. It may be empty. If I pick, see, I can let us say the vertex set I picked is an independent set. So what will be the size of EP? So Vp was picked through a random experiment. Each vertex was picked with probability p. But the set in this experiment, the set I picked is an independent set in graph G. Everyone knows what is an independent set? Yeah, means there is no edges between these vertices. Then how many edges will you have in EP? Pardon? 0, right? Only those edges will be inside EP whose both endpoints are included in Vp. Okay. So what will be the expected size of EP? An edge is being picked. So when will an edge be picked? Both the vertices are being picked. What is the probability that both the vertices are picked? P square. So on expectation, how many edges will I pick? So it will be, so I get this graph GP, okay, which is a random graph. Okay. but I will keep the drawing of the graph. So, original graph G had a drawing in the plane with exactly CRG crossing. This graph may be, there cannot be a fixed drawing for GP also, right, because each graph is, it's a distribution over graphs, right, it's a distribution over induced subgraphs of G basically, okay. So, there is no fixed drawing. So, what I do is, I will, as if I will, so let us say the original graph had some drawing like this. So, let me do it in the picture. This was your original graph. In the experiment, I picked this vertex, this vertex, this vertex, this vertex and this vertex. Okay. So, I will keep these drawings, I will keep these edges like this blue drawing. This makes sense? I am not trying to redraw GP, I am trying to use the drawing of G itself for GP. Okay. So, there will be some crossings left. So, if for, let us say for this crossing, if I have picked all these 4 vertices, this one, this one, this one, this one, then this edge and this edge will be present. This edge and this edge will be drawn in the plane as it was drawn in GP, as it was drawn for G. So, there will be a crossing in GP, right. So, when will there be a crossing in GP? So, the 2 edges that are participating in the drawing, all of those 4 vertices are picked. When all those 4 vertices will be picked? Okay. So, I am writing C prime GP as the number of crossings that I have when I use this drawing, the drawing of G. Okay. So, this is again not a fixed number, again it is a like it is a random variable. So, what is the expected value of this random variable? Each crossing of original graph G will be selected if all the 4 vertices that participate in the crossing are picked. That happens with probability p to the power 4. So, how many crossings do you have in the original one? CRG. So, this will be equal to CRG okay. Okay, so let me, so see, I mean, if I wrote this equation, so this one was coming from, I know the crossing of GP is greater than equal to number of edges minus 3 times the number of vertices plus 6 or something like this, right. This is what we proved. So, forget about the 6, I just keep this, still good enough, right. I am taking a weaker estimate, right. So, this is I know is true, right. If this is true, see this is not the exact, this C prime of GP is obviously bigger than CR of GP, right. So, C prime GP you expect it to be bigger than this also, because this one was this is the minimum crossing number of GP. This is the crossing that I am getting by keeping the same drawing of G. So, what does this tell you? This tells you that just this equation tells you, and using this we get C prime GP minus EP minus 3 VP. This is greater than equal to 0. So, this random variable is positive. So, the expected value should be also positive, right. But what is the value of this? this thing, expected value of, so this will give us expected value of C GP minus expected value of EP minus 3 times expected value of VP is greater than equal to 0. Acha, why can I write this? This is an equality. Why can I write this? Pardon? What expectation? What? Linearity of expectation. Good. So when you are saying the correct answer, speak loudly. No, you should be confident about this. Pardon? This is the exact crossing number of GP. This is the crossings that you are getting, number of crossings that you are getting by using the, by drawing the graph in the way it was drawn in G. See, I am not, this one, these crossings I am getting because I am using the drawing of G. That is obvious, high probability that won't be an optimal one, right? You don't expect, obviously there may be some other drawing that reduces the crossing number. Exact crossing number. No, this is, but both are, see, this is not exact, this is also a random variable by the way. This is a weaker random. This random variable is dominated by this random variable. C dash GP is always greater than equal to C at GP. C at GP is the crossings that uses the drawing of the original graph G. That is not the optimal crossing drawing, right? So this random variable is dominating this random variable. See, if this is bigger than this, then this has to be bigger than this. So we get this, right? So let me slightly keep, can I keep it like this? Yeah, okay. So what do we get? We get CR, expected value of C dash GP is greater than equal to expected value of EP plus 3 times expected value of VP, size of VP. So what is the value of C dash GP? It is basically CR of G P to the power 4. So let me remove P to the power 4 is 1 by P to the power 4 times, what is the expected value of EP? Size of E P square plus size of V P, this one NP. So simplify further, so we get P square P cube. So this equation is true for all P. Right? Doesn't matter what value of P I started with, this expression is true. Right? I am allowed to choose the P that kind of maximizes the, see, I want to get a better lower bound for the crossing number, right? I will try to maximize the right hand side. Okay? Either one thing you can do is you take the right hand side, find the value of P which maximizes it. The P to try is just P, take it to be 4 times the vertex set by the size of the edge set. This. Just substitute P here and you will get the bound. So if I substitute it here, I will get V square by E cube. If I substitute it here, I will get V square by E cube. Yeah, same. So if I substitute this here, this will give me omega of, this term will give me omega of E cube by V square. So this completes the proof. Is it okay? So that's why we said we are looking at, so this crossing number is for graphs where the number of edges is more than equal to or at least 4 times the number of vertices. It comes in here. See, up till now we have not used it. This is the first time we will use it. It's okay? Yeah. Good. So now what we do is we will try to prove ST theorem, similarity product theorem, using this result. So the original similarity product theorem, so now it has number of different proofs, and but this is one of like this really beautiful proof. It's really extremely nice. Original proof of similarity and product is, the paper is not long, but the proof is actually involved. So very careful calculations you have to do. This proof you don't have to do. It is a very kind of a simple, just using this crossing number cleverly will give you the proof. Okay. So let's try to prove this. So what do we want to prove? Is it will be minus, is it? Oh, okay, yeah, maybe. Yeah, it should be minus. I'm sorry. Yeah, but that actually won't matter. So this will be the this will be dominating. Yeah, it will be minus. I'm sorry. Yeah, but this will be the term that dominates anyway. Yeah. Thank you. But just replace it with this, and you will see this is the bound. So this is what we will be proving now. So you have a set of lines, n lines, and you have a set of points, and you want to estimate that I of PL, right? The estimate you want to do is this. So I can assume without loss of generality that each point lies on at least one of the lines. If it does not, then they are like that estimate is even better, right? So they are not contributing to that incidence bound. Okay. Similarly, assume each line contains at least one point. Otherwise, they are not participating. So each line will have at least one point, and each point will have at least one line going through it. Good. Now, so let's try to filter this line even further. What I do is, I will keep only those lines that contains at least 2 points. Okay. So L prime, those lines that contains at least 2 points. Okay. So now, is this true? My claim is this is I of n. This is true, right? The lines that contain 1 point will contribute at most n many incidences, at most. So this is actually like, I can write like this itself, right? It's true. So again, if I can prove a bound for this, I am done. The same kind of bound. So again, without loss of generality, because it won't hamper the bound that we are trying to prove, assume each line contains at least 2 points also. Make sense? Yes? So all of these lines contain 2 points from P at least. Okay. Now what you do is the following. So you have these lines, and you have these different points on them. Some point lies on number of lines. So, the red points are your set P, the blue lines are L. Okay. I will make a graph out of it. How do I make a graph out of it? Each red point will be my vertex. It's okay. Each red point, so let me use a different. Each red point will be my vertex. If two red points are consecutive points on a line, I will draw edge between them. Okay, it can complete, right? So, I get a graph. Do I or don't? I get a graph, right? Okay. How many edges do I have in this graph? So, if I take, say, let us say line Li, okay, let number of points contained in this lines be called is Mi. Let us say that is the case. Good. Pardon? Yeah, so these will be the edges it will contribute, like these are the, so on the points I am assuming line Li contains Mi points. Okay. So, how many edges in the graph that I have built now will come from Li? M minus 1. Good. Okay. One thing to observe is if I take summation Mi, what do I get? I of right? Yes, no? This is okay, right? Okay, good. So, the number of edges in the graph is basically summation Mi minus 1 I equal to 1 to n. So, which is equal to how much? I of P comma L minus n. Good. So, that is a so the incidence. So, you remember how did we define P comma L this set? This was like pairs small p comma small l, such as small p belongs to capital P, small l belongs to capital L, and P lies on the line L, small p. This is how we define this set, right? This was the definition. Is it okay how this comes now? It's okay. Okay, good. Okay, so this is one thing. So, let me try to do some calculation on this side. So, let us say in this graph, okay, by the way, how many vertices does this graph have? How many vertices? There are m points. How many vertices? M vertices. Yes? Yeah, okay. If the number of edges is less than equal to is less than 4m, then what do we have? We have from this that I of P comma L is less than 4m plus n. Okay? So, let us go back to the original bound. This is basically m n whole 2 by 3 plus m plus n. Right? So, this bound, if number of edges is less than this, we have that bound. Right? Good. So, if number of edges is more than this, then what will we have? If number of edges, the case 2 is number of edges is more than equal to 4m. Then here we will use the crossing lemma, the stronger bound. How many crossings does this graph have? Crossing of G is up to constant greater than equal to number of edges cube by number of vertex square. I have written this because I am ignoring the constant terms, constant factors, sorry, right. But first observe this. So, in this graph, the way we have drawn this graph, how many maximum crossings can we have? See, each crossing is nothing but intersection of two lines. So, how many can we have at max? N square, right. Now, if n choose 2, we want to be purposefully want to be less careful. I do not want to worry about constants. Okay. It is bounded by n square. Good. What about this side? E cube. What is E cube? Number of edges. What was the number of edges? I of, no, see, we have, now we will use this one again. I of p comma L minus n, right. This is exact. I of p comma L minus n cube by m square, right. So, what does this give us? I of p comma L minus n cube by m square is less than equal to n square. So, what do we get? I of p comma L is less than equal to n m whole to the power. So, I mean this is up to constant factors. So, 2 by 3 plus n. Either it is less than equal to this, or I of p comma L is less than equal to m plus n. Add these two, you will get a upper bound also, right. See, a term, if f is less than equal to g, f is less than equal to t, then f for particular case. So, there are two cases and there can be only two cases. In case 1, f is less than equal to g situation, and in case 2, f is less than equal to t. Then obviously, f is less than equal to g plus t, right, in general. Or you can take max, whatever. Max is dominant. This is a positive term. Max will be dominated by that. So, this completes the proof, right? Is it? If you have question, ask, because it's not very obvious. Yeah, so there are like too many things happening. So, you go back, try to have some coffee, rest, again check what the calculation were. It's not that hard. It uses number of different things. The proof has number of moving parts, but you have to, it's not that difficult. Once you understand how to get the, you don't even have to understand the proof of crossing lemma. Understand the crossing lemma bound, then this is not that difficult. Okay. The proof is not that difficult doesn't mean the proof is not nice. Okay. It only means that the person who came up with is intelligent. Okay. Okay. So good. So okay. So now, as I said, I won't prove it, but you can prove a similar result for point circle incidences. So L PV set of circles in the plane, P set of points in the plane, and you have similar bounds. So, this, let us say you have set of n circles, set of m points. So, again you have similar bounds. Okay, good. So, let us revisit Edosh's units, revisit. So, we have not proved anything other than ST in discrete. So, let us try to get a bound for this. revisiting Eddowes distant distance problem. So, what was the question? So, given n points, I want to know how many distant distances can it generate. That was the question, right. So, given n points in the plane, I want to know how many, no, not sorry, not distant distances, number of unit distances. Distant distance is a much harder question to, it is not going to be proved in 5 minutes like this. So, okay, so number of unit distances I want to estimate. So, I give you n points in the plane, how many unit distances can you get? Okay. So, the way to prove this is the following. So, you have a set of points. Oh, by the way, if I replace unit with length to distances, will the bounds change? Does it matter? Or let us say unit by 1.5, number of pairs with distances 1.5 away from each other. Scaled version, no, this is nothing. A unit is just, it sounds good, that is why we, okay. You can reformulate it as saying, restate it by saying number of times a distance get repeated, a particular distance get repeated, okay, in the point set. But anyway, let us stick to unit distance only. So, you have set of points in the plane. What you do is, on each point you draw a circle of length, radius of the circle is 1. Okay. So, here you will have another one here. So, let us say these are unit distance from each other, maybe I will not do that. Okay. So, let us say I add another point, then what will happen? The circle, if these are unit distance, then circle goes through this, will have this point on the boundary, circle that is centered at this will have this point on the boundary, right. Good. Okay. So, now I have a family of circles. How many circles do I have? N circles, and number of points, n points. Okay. I know what is the bound for this, n p by l, p comma l, number of incidences between these red circles and black points. How many is it? M equal to n, right. So, it should be less than equal to up to a constant factor 4 by 3, right, just from the top this theorem. Okay. My now claim is number of pairs of points that are exactly unit distance away from each other is I of p comma l by 2. So, what we use the term un, right. So, un for this point set is exactly I of p comma l by 2. See, there are 2 points that are unit length, distance between them is 1 unit. Circle centered at this one will have this on the boundary. The circle centered at here will have the other point on the boundary. So, 1 unit length pair of points is counted twice in I of PL. So, let us say you have 2 points, distance between them is 1. So, the circle, so this is the 1, this is 2. Circle centered at 2 will have point 1 on the boundary. Circle centered at 1 will have point 2 on the boundary, right. So, a pair of points whose distance between them is 1 will contribute 2 incidences to this I of PL, right. This circle circle centered at 2 with point 1 on the boundary, circle centered at 1 with point 2 on the boundary. Is counted twice. And similarly, you can argue here, I mean, there is nothing to argue, this itself is the proof, which says that so number of unit distances in this point set is exactly equals to I of p comma L by 2. Now we have the bound. We know what is I of p comma L, right? What is it? N to the power 3 by 2 at most. So up to constant is not 3 by 2, 4 by 3. So this is the bound. So I will give you one more proof, let's say, and then I will finish. Okay. So this is number of unit area triangle problem. So what was the question? So I have points in the plane. I want to know how many unit area triangles I can make with this set of points. That is the question. So how many triplets of points I can have such that the triangle made with these 3 points have unit area. This is the question that you are interested in solving. Okay. So let me give you the theorem that we will be proving. It is n to the power 7 by 3. This is due to, this is, okay, the reference I forget. If I remember, it was with Janos and I forgot. So this was Sharir, Janos and someone. More recently, Sharir with Raz improved the bound to something like this. So this is basically n square times n to the power 1/3. This is now n square times n to the power 2 by 9. So this is an improvement. So they showed number will be at least this. It has been improved to this now. Very recently, this is I think 2016 paper. Okay. This proof is actually not that hard. You can prove it. This is also not that hard, but this is even simpler. Directly ST theorem will give you. So how do we do it? Okay. Let's fix a pair of points, PQ. Okay. Look at the line that goes through them. Let me say d of p comma q be the distance between the points. Okay. Look at two parallel lines. For each pair, look at these two parallel lines. So the distance here is 2 by dpq. Okay. So if I know, see, if I know the number of points I have here from the original point set will tell me number of unit area triangles I can make. So if I know the number of points on this line plus the number of points on this line, then I know number of triangles I can have with PQ as one edge and the other vertex, and there is another vertex that will make a unit area triangle with this, right? All of them will make unit area, right? What am I using here? I am using the, what is the area of a triangle bound? Like proof, formula, half into base into height, right? So if I know the number of points here, number of points here, I am done. Good. Okay, so each pair PQ will give me 2 lines. Now let's say keep P fixed and keep varying Q. Okay. So basically I can take PR now. Again this one line, again the parallel 2 lines. Okay. Again I want to know number of points on this, number of points on this. Okay. So then if I fix P, number of Qs I can take is how many? N minus 1 choices I have. Each of them will give me at most 2 lines. So, if I fix P, how many such how many such lines I will generate? At most 2n minus 2 lines. Right, and I want to know number of incidences between this 2n minus 2 lines and the rest of the points. How many will it be? See, it is basically n lines, n, when I said up to a factor, n lines, n points. How many can it be incidences? N to the power 4 by 3. Right. So, exactly what I calculated here, number of, so these are the number of triangles, unit area triangles I can make with P being one vertex, right. Is it so? But am I double counting anywhere? Just think through. Am I double counting anywhere? See, let's say PQR, okay. So, is a unit area triangle incident at P, okay. This triangle is counted twice exactly. When I take the point pair PQ R, or when I take PR and Q. So, each triangle incident to P is counted twice. That is the at most I am counting, over counting. Otherwise, so up to a constant I am tight this bound, right. If I know the bound on incidences, okay. So, okay, so up to a constant it will be n to the power 4 by 3. Good. How many ways I can choose P? N choose 1, so n. So, n to the power 4 by 3 plus 1. Let us get this bound. So, there is a magic, okay. So, I mean that you have to be careful. Yeah. Again, the proof looks familiar because it is a very nice proof, not because the problem is simple. Specifically, this proof is more involved than the previous one. N to the power 20 by 9 is more involved than this one. Uses similar ideas, but more involved. Yeah, what else? So, I think I finish, or I will give center point. It's too much already. Huh? Okay, so that's it. Any questions? I take questions, and then I'll stop. Yeah, so I mean, we covered a lot. So as with what Arijit Vishnu was saying, so obviously we won't retain everything. Go back, play some video games or whatever you want to do nowadays. Now young people do, I don't know. Relax and then go through these notes. If you have some questions, ask us tomorrow. Okay, but these are not hard things. Okay, but there are, as I said, there are a number of moving parts. If you understand each part properly, reconstructing may not be that hard. So okay, so what did I prove? I proved that the number of unit area triangles that I can get, I fixed a point P, number of unit area triangles I can get with this as one of the vertices is n to the power 4 by 3. This is what we have basically proved. Oh, for a single point. So that is how we got the single point. So what I first did, I first picked the point P. Let's say, and then I picked a point Q. Okay. Once I fix P and Q, I get 2 lines. By the way, when I said you can get at most 2n minus 2 lines, there is a reason why I say it is at most 2n minus. I did not want to confuse you even further, because one thing that can happen is assume that P is like this, P, Q and R are like this, and the length of PR and PQ is same, and they are on the same line. Then these 2 pairs will jointly contribute only 2 lines. Okay, but we are anyway playing an overestimate game, so we don't have any problem with it. So what did we say? So the number of lines that we have will be at most 2n minus 2. Once I have P fixed, number of these parallel things that we are generating will be at most, number of lines that we are generating will be at most 2n minus 2. And I am basically interested if I can know the estimate on the number of points that lie on these lines, or no, basically know the estimate on I of PL, with P being the points and L being the lines, then I will know up to a constant number of unit area triangles incident to P. There is a double count here, as I said, PQR triangle will be counted twice, but as that's why I am saying up to a constant factor it is tight. Okay. So now I want to estimate the number of incidences between these lines and the points. So this will tell you number of unit area triangles incident to P. That we have, but that estimate, number of incidence estimates n to the power 4 by 3, right? Number of points is n, number of lines is n, so n to the power 4 by 3, right? But each, now you do it for each triangle, right? For each point P. So how many ways can you choose P? N. So again, this is an overestimate, but we want an upper bound, so it's okay. We are surely overcounting, not a problem for us. We are upper bounding, right? So by the way, what is, can you think of us, I will end by this. What will be a lower bound for this? What is it? So let's say I place like n by 2 points unit away from each other on one parallel line, like there are two parallel lines, and the distance is 2, and the n by 2 points on this side, n by 2 points on this side, and the any 2 points, consecutive points, are 1 away. How many triangles, unit area triangles will I get? Let's say n square, right? Up to constant n square. So currently the best lower bound in n square log n or log n square, I forgot. So this one was done by Edosh also with Pudi. So we proved that it grows faster than n square asymptotically. And the best upper bound we have is now n to the power 20 by 9. So there is a gap. So it's a good problem to think this evening. Come and tell me how to solve this tomorrow. Okay. Any other question? Yeah. So, but that, I mean, algorithmically, you can always do it. It's not hard, no. Worst case n cube algorithm is there. Check all cube. I mean, in discrete geometry, you are interested in trying to estimate these bounds. But see, well, like when you say exact, so what do you mean by exact? Given a point set, you can count the number of unit area triangles. There is no maximum; it's an exact number. But that doesn't tell you a bound for all n, no? Neither it tells you bound for all n, neither it, so let's say I will tell you 10 points, how many unit, taking 10 points, how many unit area triangles you can generate. But number of arrangements of 10 points in the plane is infinite. For a fixed arrangement of 10 points, you can count. But the number of possible 10-point arrangements in R2 is uncountable, no?
But if there is a specific pattern on which we arrange those 10 points and get the maximum number of.
So then you have to prove that this pattern will give you this is the worst case examples. That is even harder most of the time than getting this bounds like n to the power 7 by 3. This particular arrangement will give you the worst, this is the worst case arrangement or the best case arrangement, these are even harder problem to try. But sometimes you can do it, okay. So there are particular kind of point line, heavy lines incidences, where you know for n extremely large values, the worst case bounds are like the worst case, the point set will look something like this. We lie on some cubic curves or something like this. Okay, but those are even harder things to prove. I've forgotten this, but it's the game here is again arrangement was not the main problem. Estimating that it will be bigger than n square was the main thing, and I have forgotten. I've read it long time. I don't even remember. I read it so long time back, but I don't know. Maybe he used some number theory again here also. I don't know. I have to check the paper. I've forgotten. It's long time back. I've checked. It's good to go back to the paper and see what he did. But this is again, it's not a trivial idea. Like as with the grid case, you remember, like the arrangement was simple, but you had to use something stronger to prove that bound, right? The number of distinct distances case, right? You have to use the result in number theory. Here I don't remember now. Some time back. That's it.